Good evening. Welcome to our special on the Shaw Prize 2019. I'm Diana Lynn. The Astronomy Award goes to Dr. Edward Stone for his leadership in the past 4 decades of the Voyager mission that has transformed our understanding of the 4 giant planets and the outer solar system. It has now begun exploring interstellar space. Dr. Stone works here at Caltech.
I arrived at Caltech in 1964 to join in setting up a new space physics course.
An idea was brewing to explore the giant planets in the outer solar system.
It's a big challenge because the sun is much dimmer, there's less solar power. You need help from flying by a planet to give you an extra boost, a slingshot effect.
In 1965, a graduate student at NASA's Jet Propulsion Laboratory, that's run by Caltech, made a timely discovery.
If you launched a spacecraft in 1977, it could fly by Jupiter, Saturn, Uranus, and Neptune, all lined up on the same side of the sun, waiting to be surveyed. That happens once every 176 years.
In 1972, designs for Voyager 1 and Voyager 2 spacecraft were approved.
The first automated spacecraft that could take care of itself. It had a problem, it would switch to some backups, all autonomously on board.
Professor Stone moved to JPL as the project scientist of the billion-dollar mission, presiding over 11 teams totaling some 200 scientists.
Engaged in designing, building instruments, and then analyzing the data as it was coming in during our encounters. One advantage was that I had developed instruments which had flown in space.
Edward Stone enrolled at the University of Chicago in 1956.
And in 1957, Sputnik was launched. Suddenly there was a whole new space physics field, just waiting for instruments that could actually measure what's out there.
For his thesis experiment in 1961, he designed, assembled, and tested a telescope that was launched into polar orbit and measured cosmic rays and solar particles. It was fellow Chicago U alumnus Robbie Vogt who got Ed Stone to join him at Caltech and to head the Voyager mission. Vogt said he himself was originally offered the job, but declined.
See, when I disagreed with somebody, I let them know, I think you are not very competent. Ed, on the other hand, had the patience to bring out the best in people. I became involved when the National Academy of Sciences got upset and said basically, JPL has engineered the most beautiful, most perfect spacecraft, but it has no science instruments. JPL needed Ed Stone. From the moment he took office, he was instrumental in making sure that this spacecraft could do science.
It makes it so much more valuable to be a member of the team, to have him explain to you why this science is unique and what's important about it.
That's a parabolic antenna which focuses all the energy in a beam, and it always points to Earth to send the data. So that sets the scale, about 3.5 meters across.
The bay beneath, with its golden record cover, has all the electronics for the spacecraft. The science boom has 3 instruments.
The top one for things moving nearly the speed of light. The one down here is the low-energy charged particles. I was responsible for designing was the one for the low-energy particles. Particle would come in the top. These detectors did really wonderful work at each of the planets where trapped radiation was measurable by these 4 telescopes, which looked in 4 different directions. The third thing measures a solar wind from the sun. Out on the end was the scan platform, which could point those instruments, which included 2 cameras, at various objects as we fly by the planets and their moons.
3, 2, 1.
Voyager was launched in 1977.
Our first flyby was Jupiter in 1979, and we were surprised every day. We learned that the Great Red Spot is just the largest of many storms in Jupiter's atmosphere.
last for more than 100 years. We got up close and started taking pictures, and it was just turbulence. And that was very surprising.
All this being analyzed in real time because Ed infused his team with that enthusiasm, with that rigor, with that devotion.
He really was able to lead in a very respectful and very gracious manner.
The moons were quite remarkable. The surface of Io, with all of the black lava lakes, we had volcanic activity 10 times that of the entire Earth.
The moon Europa is covered with white ice.
There's a liquid water ocean under that icy cap that's on that planet. Perhaps there's life there. Next flyby was Saturn. Sunlight's only 1% of that here on Earth. Moons orbiting created wakes in the rings, which are in fact just icy snowballs. Moon Titan has a nitrogen atmosphere, rivers and lakes of liquid natural gas, which may resemble the early Earth before life evolved and created all the oxygen that we breathe today. On to Uranus, 19 times as far from the sun as the Earth. One of the small moons called Miranda is an icy body, but look at the number of earthquake faults. And there's a cliff kilometers high on this small moon that's only 500 kilometers in diameter. On then to Neptune, which is now 30 times as far from the sun as the Earth. So little energy from the sun. But it turns out the fastest winds we've seen in the solar system were on the very cold Neptune. Moon Triton, that's only 4 degrees above absolute zero. The really surprising thing was we saw geysers erupting from that very cold region.
Every time we went by a new planet, it was different. And we never got tired, and the surprises never stopped.
Ed is the visionary who is able to keep this together.
Ed had to know a lot about everybody's science so that he could make a good decision and try to bring him to a consensus.
He could see the strengths and weaknesses. Dr. Stone was a great leader for Voyager.
The hardest time we had, I think, was first just after launch. The command didn't get sent at the right time, and one of our receivers, which is the way we can talk to the spacecraft, stopped working. But we had a backup receiver, and that's the way we flew the rest of the mission. Another critical time was when Voyager 1 flew by Saturn. Its scan platform, which could point the camera at different things to look at, stopped. Fortunately, once again, we found a way to repair that remotely.
Dr. Stone was also the public face of the Voyager missions.
We had 6 flybys, 2 of Jupiter, 2 of Saturn, then 1 of the Uranus and Neptune each. During each encounter, we would have a routine press conference. In the mornings, I would be responsible for deciding the science part.
And the reporter put his hand up and said, "Dr. Stone, why do you always have more questions than answers?" And Dr. Stone said, "That's good. That's the way it should be. Because if you knew what the answers were before you got there, there would be no point in going there."
Ed is very, very good at getting up and giving a talk and explaining complicated things in a simple fashion.
Created a lot of enthusiasm in the public for Voyager, for planetary science. And it had a profound impact for the people who funded space research, right? Including Congress.
We had what I call the terracentric view, a view based on what we knew about the Earth. Voyager really changed our view of the solar system.
How the solar system formed and how the planets got there, carbon and hydrogen and oxygen and all the things that life is made out of.
Voyager 1, looking back at the solar system beyond Neptune. This image has in it the pale blue dot, a very tiny speck of light, which is the Earth.
Coming up, Voyager in interstellar space.
Over 1.5 million kilometers per hour of wind blowing outward from the sun, creating a huge bubble. All the planets are inside the bubble. In 2012, Voyager 1 became the first human-made object to enter interstellar space, to leave the solar bubble behind.
Always believing there's a chance that it could arrive in interstellar space. That vision caused a lot of people to start enlarging their own vision of what could be done in these sort of science missions.
It turns out that the heliosphere is a radiation shield that's protecting the Earth. There's 4 times more radiation outside the bubble than inside.
One of our big discoveries was getting to the interstellar medium and measuring galactic cosmic rays. Galactic cosmic rays are high-energy nuclei, and they're passing through your body. Their origin is exploding stars, but nobody knew the energy distribution. Ed had a lot to do with keeping Voyager going till we got there, because there was a number of attempts to save money and turn it off.
Between Saturn and Uranus on Voyager 2, I became the chair of the Division of Physics, Math, and Astronomy at Caltech, and my office was right here on East Bridge.
And in 1991, Ed Stone was made director of JPL for a decade.
We still run our lab in the evenings. We would be at the board in mid-sentence, and the secretary or somebody would come in and say, "You got to go to Washington right now." So he would take off. He would come back 3 days later, and we would just start exactly where we left off. He was an incredible multitasker.
He's very happy, and he's not bogged down by the pressures that you'd expect of people with his level of achievement.
We had to find ways to do more with less money. So it's really an exciting time. 20 different projects over that time period I really helped formulate and then learned from. We were surprised what was out there. We wanted to go back and stay for a long period of time.
The Galileo spacecraft orbited Jupiter for 8 years. Cassini orbited Saturn for 13 years. Dr. Stone remains the project scientist for the Voyager mission.
He's an active research scientist, and he's running an international consortium. He's available for students, and he presents to the public. This combination of skills is rare, but one that will advance science immeasurably.
Voyager 1 is now something like 22 billion kilometers from the sun. Voyager 2 is at about 18 billion kilometers. The power for the spacecraft is these 3 radioisotope thermoelectric generators. It's plutonium-238. Natural radioactive decay creates heat, and heat is converted into electricity. We will be out of power between 5 and 10 years from now for all the science instruments.
What will the Voyagers do then?
Every 225 million years, they will make an orbit all around the Milky Way, and they will be doing that for billions of years.
A great strength of Ed is the mental discipline to be able to control how much time he spends on each and succeeds.
I'm really interested in helping people realize their dreams. I've had a wonderful journey myself in terms of discovery.
It's pretty amazing to encounter a lot of people who respect him and love him.
Sure. He has a very cute smile, a real funny sense of humor, and a very gentle, kind person.
A gentleman in every respect. He is the smartest person I've ever been around.
He's a really cool guy.
Ed is indefatigable, and he runs across campus, people chasing after him.
Very fast, from one meeting to the next, zoom, 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 the Energizer Bunny.
Nobody knows what he looks like, because when he's coming towards you, he's blue shifted, and when he's going away, he's red shifted.
Ed Stone is the fastest particle in the universe.
Ed grew up in Burlington, Iowa, where his father was a construction superintendent.
He built schools, hospitals, churches. I just kind of got to learn from him about how interesting it was to know how things work and how to fix things. I built radios, I built high-fidelity systems. So I was a hands-on building what in those days was advanced technology.
Ed's mother worked in their family franchise business.
Later on in life, she was painting china, which she contributed to her church. I found it fascinating that you could actually calculate things, you could actually design things. I just sort of grew up thinking I would like to be a scientist.
His physics teacher recommended the University of Chicago.
He says it's a very high-rated physics department and would work very well for me.
It did. Ed met Alice from rural Illinois at Chicago U.
I got a scholarship, probably majoring in English. We met on a blind date through mutual friends, and it clicked.
Did you like her the minute you saw her?
Oh, yeah, yes. we had similar backgrounds and similar kinds of families, so it was a good, very easy match. She was really smart and interested in what I was doing.
He was smart, funny, just as skinny then as he is now. My parents were a little uneasy when they sent me to Chicago, but when they found out that Edward's grandfather was a Methodist minister, they decided maybe he was a good person for me to know.
The couple married in 1962.
He did not get down on one knee and propose. It was just that we were talking about our life in the future, and it was just a decision for the two of us to get married.
The family moved to California when he joined Caltech. While raising two daughters, Alice obtained a bachelor's degree in business administration and worked as a freelance writer.
During Voyager encounters, he would bring his work home in the form of photographs that had been taken just that day and show them to us over the dinner table before they were released to the press the next day. They were overwhelming.
This was really a journey of discovery. My family were part of that whole journey.
That was very exciting. The kids loved it.
We would go to JPL when they had what are called encounters, watch the pictures come in. It was awesome. I have great memories of that.
Growing up with my dad was always an experience in learning. As a dad, he is gentle. He is very well-intentioned in his earnestness in finding out about us.
And then when our grandsons came along, they also had a chance to share it.
I was raised on space. We had space placemats and Pluto was still on there. You start seeing old footage. I see videos of my grandpa, like on TV. And you know, he's giving announcements and I'm like, that's my grandpa.
I think his work is fantastic.
Yeah.
I think we both think his work is fantastic. This is probably the second most important science project that's ever been accomplished by humans, second only to going to the moon.
I was proud of him. I was proud of the whole Voyager team. All those dozens and dozens of people worked very, very hard. Sometimes they slept at the lab overnight. It is immersive. They lose themselves in it. And so that's what drives them.
His work ethic is like, to me, like the ideal, and that's something like I strive for even to this day.
When I first met him, I quickly learned that it's a pretty big deal and he's done a lot of impressive things.
Probably the smartest person I've ever met, but he manages to not be arrogant about it.
He's a very humble person. He enjoys the simple things in life. He enjoys a beer in the afternoon. He enjoys his family, I hope.
We go on vacations with Ed and Alice every year. They are perfect in-laws. They're there when we need some help, and they kind of let us handle our lives the rest of the time.
Very self-disciplined, but also very full of genuine joy in what it is that he has done with his career and his life.
There is not much leisure time as far as Ed is concerned. There are no hobbies.
My real hobby is what I do. It's real work, but for me, it's a hobby.
Lately, he's been at home, which has been very nice. We would both sort of like to take a cruise on the Mississippi River up through the area where we lived.
But Ed has no plan to retire. He had worked for 24 years on 2 10-meter telescopes at the Keck Observatory in Hawaii.
They're currently the most productive telescopes on Earth because they can see the furthest out into space. We're now starting to design is a 30-meter telescope. It's 81 times brighter than what Keck can do. So this will allow us to see the first stars in the universe as they were forming, as well as looking at planets around nearby stars.
But the project is disrupted by protests from native Hawaiians.
When I look up at the sky, I think of where are the frontiers? Where do we go next to help us understand everything about the nature around us here on Earth and in the solar system and in the other planetary system? The frontiers out there are immense. There's a science frontier, there's a technical frontier. We are never going to visit it all.
Good evening. Welcome to our special on the Shaw Prize 2019. I'm Diana Lin. American biologist Maria Jason won the Life Science and Medicine Award for her seminal work in DNA damage and repair in mammalian cells, which has wide implications for genome editing and cancer treatment. Maria lives and works here in New York City. Our chromosomes are constantly attacked by agents damaging DNA. There are 2 strands of DNA, so encoded information has its own backup.
Maria was the first to show that you can make these double-stranded breaks, and then it's possible to repair that in a way that you can change the information of the cell.
The failure to repair damaged DNA faithfully can lead to many human diseases.
Maria is driven by understanding genomic integrity.
Our cells protect ourselves to preserve the information they've inherited from mom and dad.
My father emigrated in 1951 from Czechoslovakia.
Her mom's family came from Iraq.
Neither one of them had any college at all. Typical of immigrant families, they see education as the way to move forward.
Maria attended Florida Atlantic University, where she was inspired by molecular biology courses.
Math was my favorite subject for quite some time. Molecular studies often are really focused on measurable quantities, and so a feeling that you could really understand a process and feel confident about results.
Maria obtained her PhD at the Massachusetts Institute of Technology.
Of course, a concern for me was, what will I fit in?
She was at that time quite insecure.
Professor Paul Schimmel was her thesis advisor.
But the energy and excitement of being there, those were some of the best years of my life.
She had a very strong root in herself from the kind of support that she had at home from her father, who raised her.
Maria's mom died of breast cancer when she was 8. For her thesis, Maria worked with the bacteria E. coli.
I used these new tools of in vitro mutagenesis to knock out the gene I was interested in, to mutate it so that there would be no functional copy from the chromosomal sequence. So I could just put in my own pieces of the gene and ask where the function was.
Maria participated in 8 papers published in grad school.
I was really keen to do gene modification experiments in mammalian cells. I thought this would really open up a whole new frontier.
For her postdoc in Zurich, Maria used a study in yeast.
If there's a double-strand break, the ends of the DNA can capture sequences from the chromosome. And so I had a study of this using the virus system, and I found, in fact, yes, a double-strand break in the viral genome would greatly increase homologous recombination.
Her second postdoc was at Nobel laureate Paul Berg's lab at Stanford.
Finding that double-strand breaks are highly promotional for recombination it was an important breakthrough.
Maria then experimented with having double-strand breaks integrated into the viral genome.
That worked very well. We could get a 100-fold increase of the plasmid going into the correct site in the genome. But still, it was not that efficient.
In 1990, she moved to the Memorial Sloan Kettering Cancer Center in New York City, where she established her own lab.
What was clear to me was that to really impact recombination, the DNA damage in the form of the double-strand break is introduced into the genome, not into the plasmid DNA. And the cells want to use the broken molecule for repair.
A real challenge was mammalian genomes are huge. Maria managed to get a suitable nuclease from a French lab to create a double-strand break in a mouse genome.
I was just stunned by how well things worked. I had hoped we'd get a stimulation of recombination, but it was between 1 and 10,000-fold stimulation. A very interesting sideline, very powerful, is that besides this huge stimulation of homologous recombination for very precise genome modifications to use, for example, to cure a disease, we had also seen these non-homologous end joining events, and these are the ones that would create mutations in genes very efficiently.
Many people in the field believed that non-homologous end joining was the most important pathway in mammalian cells. Maria was really one of the leaders in showing that homologous recombination is actually really critical in cells. She had to stand her ground.
When we did these experiments in 1994, basically what's now termed gene editing, I thought this was a game changer. This would be the most important paper from my earlier career, but we went to about 5 journals before it was finally published, so it was kind of heartbreaking to me. That was the time when people could take approaches to modify the genome that were inefficient, but they thought, okay, that's good enough for now.
Now, various systems make it easy to have appropriate double-strand breaks to promote recombination.
The development of the CRISPR system makes the importance of what Maria discovered and established that much more important quickly.
Almost all modern gene therapy efforts, all the gene editing, all the research done in correcting genomes are done on the basis of that fundamental discovery she made in 1994.
Here we are today, using her discovery to make better crops, animals for a safer and more ethical agriculture, understanding human cells better.
That allows you to target any sequence in the genome and either replace it with a new sequence or correct a mutation that's present from birth.
If you can specifically repair genes that are mutated, you could cure diseases.
The hope is that those discoveries are going to be the things that are going to fuel inventions of drugs.
Right now, problems focus on misuse of the technology.
We shouldn't use it to play around and see what happens with humans.
In recent years, Maria's lab did experiments on hereditary breast ovarian tumor suppressor genes BRCA1 and BRCA2 using mice.
These experiments really indicate how prominent homologous recombination is in mammary tissue and presumably in the human breasts as well, especially during times of rapid proliferation, for example, in puberty or during pregnancy.
Experiments were also done on human cell lines.
What we find is that in the absence of BRCA2, there are lots of aberrations in chromosomes, so it certainly raises the question, how do these cells survive to form tumors when they've lost BRCA2 function? And how can we, importantly, target those cells or prevent them from occurring in the first place?
She devoted most of her time for the research, go back home very late, almost every day, including weekend, holiday.
Most of us are workaholics just because we're so motivated.
Maria Jason was extremely bright, ambitious.
She's extremely honest. Whenever I say something wrong, she'll say, this is incorrect. She would not try to be polite.
She's creative. She starts things from nothing.
Maria is a star and never acts like one.
Very warm and loving person.
A colleague's dad recently passed away.
She was so upset, and then we decided to plant a tree in memory of his father.
She know my family, know my kids since he was born in New York City.
She always makes a point of visiting former trainees when she's in their part of the world, and she brings gifts for the kids.
I love traveling and going to international and national meetings.
She's very adventurous about seeking out local cultures, food and drink, and so it's always been good to tag along with her.
I have a particular soft spot for France, hiking around the hills in Provence or swimming in the Mediterranean in the Côte d'Azur.
My sister has had a sense of curiosity about all sorts of things as far back as I can remember, and an openness to seeing things, people, the world differently. One of the most important things in my life is how close we've been as sisters. What a loving and generous and thoughtful sister you've always been.
Both love dogs.
We've managed to co-share 6 dogs between us, how they respond to people and situations. Scientifically, it's very curious for me, as well as they're very loving creatures. I would like to continue making scientific discoveries. You know something about nature that nobody knew before, and so I just find that extremely stimulating.
The Mathematical Sciences Award goes to a French researcher for his prolific and insightful contributions to probability and high-dimensional geometry. We met up with Michel Talleyrand here in Paris. Michel Talleyrand came to Paris in 1974 as a mathematical researcher.
These are called the 30 glorious years. In French economy was growing 5% a year, so there was money for 17 positions at the entrance of CNRS.
The French National Center for Scientific Research, where Michel stayed until he retired 2 years ago. Michel grew up in Lyon, where his father was a maths professor.
He tried to interest me in mathematics, but I was not so excited.
His family has defective retinas due to a rare gene.
I lost my right eye when I was 5 years old.
At 15, he suffered 3 retinal detachments and missed school for half a year.
That's the time I really focused my energy on studying. I became a good student, at least in math and physics.
Michel attended Lyon University.
I took the books and I solved the problems. You train yourself, it becomes easy. You start to see the beauty and the challenge and the complexities.
CNRS sent him to join Professor Gustave Choquet's group at the University of Paris 6, where Michel later earned his PhD.
First advice he gave me, doing research, ask a problem in this simplest setting where it makes sense and forget all the extra structure. Salut!
Michel says he applied that advice when he was handed a problem by Gilles Pizier, who joined the group in 1983.
In probability Gaussian processes, the question emerged to find a characterization of the processes which are given abstractly, and you want to know if they have continuous path. I could see that I was not going to solve it.
The important thing is you have 2 quantities of different natures. This is geometry, and here this is probability. You want to estimate this number in function of geometric characteristic of that space.
The problem was made popular by Xavier Wernicke.
He proved that the supremum of the stochastic process here, it's always bounded by some constant time, this geometric quantity. What I proved is an inequality goes the other side, is that in fact these two quantities here, they are always of the same order. And the reason this is a good theorem is that it applies in complete generality. The 1985 result I proved is called the majorizing measure theorem to completely understand the supremum of the process.
It's really a very beautiful result because of the generality and the elegance.
But the discovery I made much later in 1999 is that you don't need majorizing measure. You can use instead another idea, which I call now the generic chaining. That's a simple proof of this inequality. Now, any probability student can learn that in a few hours instead of having to struggle for months. Starting 1985, I had a really good period for 10 years. I had two ideas I liked every year.
The ideas include his first concentration inequality discovery.
7 different steps that I lived essentially 7 weeks in a totally blissful state because I know it's a completely new direction.
In dimension 2,
a point here is further than t from any point of A. In dimension n, the volume of the part of the point which are far from A becomes extremely small. That's quantified by an inequality, which is a concentration inequality. And the work I did is on the word far. Concentration inequality I proved do not fluctuate too much, and in a sense are nearly constant. What is called now the Talagrand convexified inequality, which is a half page long, something looks rather simple. I hope that this will be useful for a very long time.
Another significant breakthrough is in a problem with spin glasses.
Amorphous glasses, but with very special magnetic properties. In physics, starting from a real situation, you try to find a simple model.
In the late 70s, physicist Giorgio Parisi found a model.
He invented an extraordinarily complicated structure.
It's a very, very strange solution. People didn't know how to prove his result.
I prove that Parisi formula is true.
In Talagrand's mean field model.
The important thing is, you see, the problem was stated in purely mathematical terms. This is not a problem of physics. This involved only flipping coins. So it's really a problem of pure probability.
Everybody was astonished that mathematicians could establish this very, very important result.
The amount of mathematics that he produced is amazing, but the consistent level is very, very high. Unusual.
Actually, a lot of my work has not been read. Probably it's not as interesting, however hard it is for me to accept that. It's a book, it takes years if you want to understand. It took all my life to formulate the idea.
Professor Talagrand is curious of many things.
He's just written a book on quantum field theory.
What the physicists explain in their own language, I'm explaining in mathematical language. And it's an extremely difficult job of translation.
The main virtue of the book will be mathematically correct and deductive. This is quite demanding.
I demand a lot on myself, and of course I demand a lot on the people who are around me. Everything she touches becomes beautiful. This is the handicraft production of the family.
Michel was working constantly. He got sick, so I thought maybe it's a really good idea to take his mind off from math.
I completely concentrate on this little piece of glasses. There are some of my papers that she had made the binding. I love being with somebody who is so talented.
In 1979, Michel was visiting Kent State University in Ohio when he met Korean math PhD student Won-Soo Ri.
I was interested in the first look because she was so pretty at the time, and I couldn't resist.
On their second lunch date,
I proposed her, and she said, "You are crazy."
I think
the project of having her consent to marry me was the most difficult of my life.
A clincher was this Hong Kong-made pearl necklace.
He himself chose individual pearls, all these teardrops or something of this, so it touched me greatly.
Try and try and try again.
He doesn't have a perfect vision, but he has something much deeper. He sees it.
Time and mental energy is what is in short supply for a mathematician. She didn't take a minute of my time, and she didn't take any of my mental energy.
They married in 1981, the same year Wan Su began teaching management science at Ohio State, until she retired in 2005 and moved to France. They have 2 sons, Eugene and Daniel, and 2 grandkids.
Hey, bonjour, Elodie. How are you? Felix, bonjour, Felix.
We traveled a lot when I was younger. His hope was that we would be able to reintegrate the French school system. We were taking American classes, so we would get up 6 a.m. every day. We would study French. And so he spent years and years teaching us as a private tutor.
Eugene and his Taiwanese wife, Jamie, are software engineers living in Seattle.
He made all these puzzles on his own. He will sit down with kids for hours, just doing all the puzzles. So I feel my kids have pretty good logic sense.
My father would teach me how objects work, watches or cars or things like that. That helped spur an interest in science, and which led me to become an engineer.
Daniel played the saxophone. Michelle would take him to practice in the darkened basement.
He'd be there turning the light on every 3 minutes and studying math at the same time.
A musical family.
When we were going out, he bought me a piano.
They bought this piano together on their 10th anniversary.
The day of delivery, Michelle was so happy that I could have this piano. He was shaky.
Michelle bought her organs too. They've traveled to 110 countries.
Either we see a magnificent marvel of nature, or we see some remain of past civilization. Time together with the family, this is #1 priority. All the 3 times we had was together and with the family.
Michelle, the ran for marathons, and then we all go, even the Eugene and Daniel, they participate in the children's marathon.
Between age 30 and maybe 55, I really run 10 kilometers a day, basically.
And now?
I climb the stairs in my building, 88 stairs. Takes about 20 minutes. Very efficient way because I don't have to go to the gym. When I approved the Parisi solution, I took my children to a fancy restaurant. I was 53, I know I will never solve again a problem of that size, so I celebrated. The solving is over. Now I'm writing these books and rewriting them, and there is another kind of pleasure.